Hey, welcome back. So we're still talking about magneto-static fields, and in this video we're going to define magnetic flux density, which is going to take us to our fourth and final of Maxwell's equations in static fields. Maybe the most interesting of the four, most intriguing I find anyway. So let's get started. Now recall for electric fields, we had the electric flux density, which for free space we defined like this. Okay, that was free space. And we're still talking about free space for magnetostatic fields. So we're actually going to define something very similar. We're going to say this vector field B is mu 0 times H, the magnetic field intensity. And so we're going to call B is the magnetic flux density. Okay? And remember why we define D and why similarly we're defining B then. And that's because these things behave differently in different materials. So, while we use epsilon 0 in free space, we used a relative um, permittivity in different materials. And so we're going to do something very similar for magnetostatic fields. We're going to define this magnetic flux density with this parameter, this constant mu 0, and then you'll see that mu 0 is actually going to change for different materials. In free space, this mu 0 is 4 pi times 10 to the minus 7 henries per meter. So you can compare that with epsilon 0, which was for the electric field, which is farads per meter. So now Henry was the unit for inductance. And we're going to call this parameter here, this constant mu 0, we're going to call this the permeability of free space. Permeability. Okay, so it is constant, it's positive, so that makes the magnetic flux density B in the same direction as H. We're just it points in the same direction, parallel. Okay, now then with magnetic flux density defined, and we can define this, or we can give this units. We're going to call the units here to be Webers per square meter. Okay, we're going to call the Webers per square meter, and what we call a Weber per square meter is actually also a Tesla, which we use as capital T. And then when we have the magnetic flux density, then we can of course talk about magnetic flux. So remember we used psi for flux, but here we're talking about magnetic flux. And so that is defined as the magnetic flux through a surface is going to be the integral over that surface of the density, the magnetic flux density, dotted with a surface element, like that. This is the magnetic flux. And that integral should make a lot of sense to you now, why we use the dot product and so forth. And the magnetic flux, we say, has units of Weber. So this is how actually a Weber is defined. So if we're going to define a Weber like that, then of course the flux density then has to have Weber per square meter. So as we said, the flux lines then are parallel to B everywhere, right? Just like we said about electric flux and being parallel to the electric field. So the electric flux lines are parallel, or excuse me, the magnetic flux lines are parallel to the magnetic flux density and the magnetic field intensity lines everywhere. So for example, let's consider a current carrying wire, just a straight wire that's coming out at you. So we would represent again like that wire like this, we'd put a circle and then a dot in it. That means a vector that's coming out at you. So that's our current I. Then the magnetic field intensity, the magnetic flux density, the magnetic flux, all points in the same direction, and so we give those magnetic flux lines, this direction, in the direction of the magnetic flux density. So that would be I keep saying electric. That would be the magnetic flux line for this current. So you can imagine from the right hand rule, you point your thumb in the direction of current, which is coming out at you, and then your right hand fingers then would curl in the direction of the magnetic field intensity. So that's counterclockwise. So that's also the direction of B, being that they're parallel, magnetic flux density, and so we would call that a magnetic flux line. Now, as you know from our calculations of such a magnetic field intensity, that the magnetic field decays as you get further from the source, which is the current. So what you would say, or what you would draw, is approximately the lines would get less dense as you get away from that source. These should be circles, by the way. So show less dense circles. And again, that means that the magnetic flux, or the magnetic flux density, is getting less dense as you go outward from that current carrying wire. By the way, these arrows also represent the direction a compass needle would point towards if you were standing in this magnetic field and you had a compass. Right? And remember, what we found was that the B or I guess we found H, but B is parallel. H is perpendicular to the distance vector from the wire. So let's say we have a point here, we're standing there, and here's our distance vector from the wire. Remember that H is perpendicular. That's how I arrived at these circles, by the way. We've talked about this. So that means that at that point in red, the field is pointing this way, right? And so at every point that's true. So you're going around in a circle like that. The magnetic field intensity points like that. Now, when we talked about electric flux, we would also talk about a monopole, which was, remember this guy where we had maybe a positive Q, and a positive Q gave flux lines like this. Right? So for magnetic fields, we can talk about magnetic monopoles. So again, this was electric. That was an electric monopole. We talk about magnetic monopoles. And an magnetic monopole would be an isolated north or south pole. And again, this is similar to positive charge, like protons, or a negative charge, electrons. And I say it would be that case because actually no magnetic monopoles have ever been discovered or created. It's safe to assume they don't exist. If you take, for example, a bar magnet, which has a north and south pole, and if you cut it in half, it turns out you get two bar magnets, each with a north and a south pole. You cannot separate a north pole from a south pole. Wherever there's one, there's the other. So that's all to say again that there are no magnetic monopoles. They do not exist. Now, in keeping with this parallel, or this analogy to electric flux and electric fields, remember that Gauss's law said that the total electric flux through a closed surface is equal to the net charge enclosed by the surface. Remember that? I'll write that down. This was Gauss's law. This was the electric flux density. The integral over a closed surface equals to the charge enclosed by that surface. So now we can write a similar thing for magnetic fields and magnetic flux density. Since the net charge if you want to think of charge in this case as magnetic charge, like monopoles, since the net charge must be zero then, because you cannot separate a north from a south pole, then this integral is always equal to zero in the magnetic case. So this integral becomes the closed surface integral of B, the magnetic flux density dotted with ds, is equal to zero. Again, because if you have a closed surface, it has to contain a north and a south pole. So the net, I'm using the word charge here for magnetism. The net charge enclosed in that surface is zero. It always will be that case. If you have your bar magnet like this, well, that's not allowed because then that surface is not closed. Okay, so any flux line that originates, that comes out of the north pole will come back into the south pole. So the net flux through that closed surface is always going to be equal to zero. So this equation that I've written down here, this is like Gauss's law, but for magnetism, and it says that there are no magnetic monopoles, essentially. Now from the divergence theorem, which relates a closed surface integral to a volume integral, the volume enclosed by that surface, then we can say that the integral over a volume then of the divergence of B is also equal to zero. And so if that's going to be the case for any volume, then this means the divergence of a magnetic field is equal to zero. There are no magnetic monopoles. So both of these equations say the same thing, right? Just as like Gauss's law had an integral form and a point form, this Gauss's law for magnetism also has an integral form and a point form. They both say the same thing. This one makes sense more physically, and this one is easier to compute mathematically. And that together is our fourth and final Maxwell equation for static fields. So let's summarize Maxwell's equations for static fields. In the electric case, we had Gauss's law, which looked like this. So this was the point form, and then I just wrote it down up above, the integral form was equal to the charge enclosed, and we can actually write the charge enclosed as a volume over the volume charge density. Okay, so that's Gauss's law. Now we just saw Gauss's law for magnetism is that the divergence of B is zero in point form, or what we just wrote down, the closed surface integral of B dot ds is equal to zero. There are no magnetic monopoles. Then for electric fields, we found that the curl of E, for static fields anyway, was zero, or the closed line integral of E dot dl was equal to zero. The interpretation of this equation, or this pair of equations, is that the circulation of an electric field around any loop is zero, and that implicates Kirchhoff's voltage law. If you go around a closed loop in a circuit, the sum of all the voltage drops must be equal to zero. Then for magnetism, recently we saw that the curl of H is equal to the current density in point form or in integral form. This was Ampere's law. The circulation of H around any closed loop is equal to the total current enclosed by that loop, or the integral of the current density dotted with the surface element. So that's it. That gives you a good idea of Maxwell's equations for static fields. Of course, this is not the most general form of Maxwell's equations. we have, we have the time varying fields that we need to get to. But before we do that, we're going to consider something called magnetic potential, which is related, well, which is kind of the analogy to potential in electric fields, right? And then we're going to look at magnetism in materials, which is very interesting. And we did this for electric fields. We're going to move from free space now to materials. So I'll see you in the next video on magnetic potential.